So inverse functions, inverse meaning opposite, so the inverse of addition is subtraction, the inverse of multiplication is division, and all of that. So inverse functions is just the opposites. So when you're looking at just a list of coordinates or a table or anything like that, remember this is x and this is y. So inverse is we're just going to literally flip them. So it's going to become, instead of x, y, we're going to turn it into y, x. So 1, -3, nothing changes. It just literally switches seats. Now you have just written the inverse list of coordinates. That's all there is to it as far as coordinates are concerned. Which the fun part is if you understand the coordinates, you can get the coordinates from Desmos for the equations and check yourself. If it's asking for the equation, that won't help. But if it's just asking, are they inverses or not, you can get the tables from the equations and do the same thing. So like number 2, again, we're going to take x and y, and we're going to turn it into yx. So 7 is now going to become my x value. -5 is now going to become my y value. -8 is my x. -6 is my y. I'll say it again. Nothing changes signs. So positives and negatives don't change. They just switch seats. So whoever y was now becomes x, and whoever x was now becomes y. Tables and coordinates, in my opinion, are like beautifully, amazingly easy. If you were to graph these in Desmos, so make the list of that first set of coordinates, and you were to graph the y equals x is probably easier because y equals is what we're used to graphing. Everything reflects over the y equals x line. And that's your perfect diagonal running through the origin in a positive direction. So a mirror image over that line should happen whether it's coordinates, whether it's an equation. The only ones that get a little weird is your quadratics and your square root functions because of rules. Like you'll see down here, it says y has to be greater than 0 because root functions just don't cross into the negative y unless there's transformations that have occurred to them. Now here's your steps. You're going to write them down later in the week too. But if you have paper, write them down. So number 1, we're going to switch the x and y. And I'm making these real simple. Number 2, solve for y. So in this case, it's in form of y equals. If it was to be in the form of f of x equals, I suggest rewriting f of x or putting a y on top of the f of x, just so your brain doesn't get overwhelmed. No difference. We're going to switch them. So it's going to now become x equals 3y plus 2. Now I need to solve for y. So line of great divide, if you have me in math 2 or any other classes prior to now, my stinky kid is my y. We're going to take the inverse of that positive 2. So we're going to subtract 2 from both sides. And that's going to give me x minus 2 equals 3y. And I've asked it a ton of times, but 3y is what operation? What is 3y operationally? So the addition, subtraction, multiplication, or division, the way it is right now. Do I need to ask it in a different way? Do you understand what I'm asking you? What operation is 3y notating? Yes, good. And it is multiplication. And that seems silly, like a silly question, but even the question mark when you typed it is because we've gotten so used to just treating it away. We don't understand the why we're treating it away. Because if I asked you, how do I get the 3 off the y? Most of you would have like quickly said division. But then I'd have to ask you the why. So we're trying to go back and make sure we understand that's 3 times y. So the inverse is division of 3 on both sides. So these 3 are now gone. And so y equals x minus 2 all over 3. That is the inverse. If this was written f of x equals 3x plus 2, the inverse is f of -1 x. That -1 means inverse. That's all that notates. And it can be g of x, k of x, all the letters. Remember, any of the letters are just noting that there is a separate, like identifying which function it is. Like I always like to say g of x is Gertrude and f of x is Frank, especially for like piecewise like we did earlier, or function notation back in math 1. So you're going to, the hardest part is remembering all your rules for solving and isolating variables, which hopefully is not super hard for most of us. The next one, he's a little bit messy. So we're going to switch our x and a y. So it's going to be x equals 2/3 y minus 5. And now we're going to solve for y. We're going to undo that minus 5. How would I move that minus 5 to the other side? What operation would I do? What's the inverse of -5 or minus 5? Yep, we're going to add 5 to both sides. Perfect. Add 5 to both sides. That x and that 5 are not like terms, so we're just going to write x plus 5 equals 2/3 y. Depending on who your teacher was prior to me, and you'll hear me say this a lot, you're in Math 3. You've had lots of great teachers, hopefully, along the way, so I don't want to unteach anything that you've learned. Some students find it easy to multiply by the reciprocal for that 2/3, so just flip it on both sides, or we can take it individually. And that division of 3, we're going to multiply both sides by 3. So the 3 goes away. And then we end up with 3x plus 15 equals 2y. And then we're going to divide by 2 because remember, again, 2y is 2 times y. And then this whole side is also divided by 2. And so our answer, again, if we'll call this g of x equals 2/3 x minus 5. Then g of -1x, so the inverse of g of x is going to be y equals 3x plus 15 over 2. The ones that get a little funky that I've seen people mess up are the last 3. I will show you those on Desmos so you can see how to check your work as well. Does anybody have a question about 3 and 4, why and how I did things so far? So the inverse function is just that perfect function reflected over the x equals y, or y equals x. All right, so we're looking at the next one. I'll switch colors because they're getting all tight. We're going to switch our x and y. So x equals y squared. So we're not switching the squared, just the x and y, plus 5. Again, line of great divide. Solve for y. What are we going to move first, and how are we going to move it? What number and how? How am I going to move that 5? Yep. Thank you so much for not leaving me hanging. I appreciate that. So x minus 5 equals y squared. Do we remember what the inverse operation of squaring something is? You should have done it in Math 1 a little, probably in Math 2 though. The inverse of squaring something. If you have a TI 83 or 84 near you, it's on the same button. You just have to hit second to get it. Does anybody remember the inverse of squaring something? I feel like I'm pulling teeth. So it's going to be square root. So my answer is going to be y equals the square root. Pay very close attention. X minus 5 is all under the square root bar. That matters because think about your transformations. If 5 was on the outside, that's the up and down slide. If it's on the inside, that's a left-right slide. Totally different graphs. So the whole thing is square rooted to get the square off the y. So this is now the inverse of x squared plus 5. Now, hopefully you're going to still see, I'll bring Desmos over because this is the one that most people get confused. If they get the solving right and then they put it in, they think they made a mistake. So inverse, again, as I said, it's a reflection over the y equals x. So that line, top and bottom, is where these graphs should match. They should mirror each other. So our first one is y equals x squared plus 5. Now, just a call out, don't have to do this, but just for in general manipulating Desmos, if I call this f of x, If you put in f of negative 1x, so the correct notation of inverse functions, it won't graph it. But we're going to call it g of x, which is not like mathematically sound. It's not the way you're going to see it on an EOC. It's not the way you're going to see it on a test. But it differentiates to desmos if I want to make a table for each, or if I want to try a coordinate for each. So like thinking about piecewise functions, a way to use this to make piecewise easier. And our answer was square root, which I need to get from our keyboard. Sorry, words are gone. Keyboard here. Square root. Whoops, that's not in the right place. We jumped. Square root of x minus 5. Again, making sure that I am still under the root bar. So what you should see now is a perfect reflection. This is not a full parabola on its side because of the rules of this not being allowed to be in the negative, because it's a square root function. And like I said, if you wanted to check it, you could go over here and do table and table. This one's not as perfect. But so theoretically, if I put in these numbers, you should see a kickback of both. So let's see, that was like 6. So if I plug in 6 here, remember the y becomes x, and I have a 1, and that's 1 and 6. If I plug in a 9 here, I should have a 2 output because that's flipping those last 2. If I plug in a 5, I should get a 0. And I do. And the negative, you're not going to get your negatives because if you see these dots are starting to pop up as well, you can check them across each one. So again, perfect reflection over the y equals x. The parabola is going to give you a half, just an arch, and vice versa. So if you started with a square root function, the reflection is going to be a full parabola because it reflects over the x equals y. So again, let's go back. Just algebraic mistakes I've watched students make. So if we're looking at our next one, what's the first thing, the very first step we should do? Hopefully you wrote it down or you're paying attention. What's the very first step you should do to be able to solve for the inverse? It's also in the corner on my paper. Yes. Eli, you were the dude. Thank you so much. So we're going to switch our x and y. X equals y minus 3 squared. Now we have to solve for y. Our first problem is the squared right now. So we're going to square root both sides because that'll get rid of that squared. And so now I have the square root of x equals y minus 3. To get rid of that minus 3, we're going to add 3 to both sides. This is not underneath the root bar. That's where you're going to run into some confusion. Make sure you put it in correctly. Into desmos, this answer is not the same as this answer. Like I said, this is a left-right slide. This is an up-down slide. This is the correct inverse for this equation. This is still going to give you that half curve, not a parabola, where you're going to have a parabola here. That's your parent function just slid to the right 3 units. This is going to give it, and it's going to be slid up 3 units relative to the parent function of square root of x. This is going to work very similarly, but we're starting with that half instead of with the parabola. So we're going to switch our x and y. X equals the square root of y minus 2. Now we're going to solve for y. We got to get rid of that root. So we're going to square both sides, which gives me x squared equals y minus 2. We're going to add 2 to both sides. So these 2's go away. And that's going to give me x squared plus 2 equals y. Again, this is a quadratic parabola up 2 units. That's the inverse function of this function. And again, you can plug those into desmos and check them. It should reflect over our y equals x. So if we type these guys in, and that was, we were given y equals 2 x And again, you don't have to do f of x, g of x. That's just if you want to manipulate it to do something for you, so it knows which one you're looking at. This was the given, which hopefully we see is that hump we've talked about, y equals, and then x squared plus 2. And so again, you're going to see that at 0, 2, the inverse would be 2, 0. And those are going to be the inverse of each other. Okay? So using desmos is a great way. So what if, verify that they are inverses. You could graph them and state that they reflect over the y equals x. That is a way to verify. Also, you can solve them and check them to verify that they are the inverse of each other.